So now we'll take a look at a worked example regarding the current chopping. And the scenario that we have is we've got a situation where I've got a reactor. We're not really told that this is a transformer or whatever. It's just simply an inductor. And this inductor has some capacitance that's associated with it. And so what we're going to be doing is we're going to be switching this off at time equals 0. To make this a little bit more complicated, what I've done is I've included a source impedance in here as well. And the relationship between L2 and L1 are such that we probably can't just assume that when the switching action occurs that we're at a voltage max. Okay, so I'm going to have to make some compensations for that in the worked example. We'll assume in this case that we got a 7.2 kV supply. And so this is kind of like line to neutral value for 12.47 kV. So this is single phase. And the breaker is going to chop a current of 1 ampere. So basically when that breaker operates, it chops 1 amp, and that 1 amp gets transferred over to the capacitor. And then I'll rework this if we have a resistance in here of 10k ohms to see what difference this makes. So for this particular problem, like say this was for a 12.47 kV three-phase circuit. If we convert this over to line to neutral, that 7200 volts is the RMS value. Square root of 2 is what we need to do to convert that to an instantaneous. I'm going to go ahead and just use a sine reference for the source. So this is 60 Hertz 377T, and the point in wave is going to be theta in this case. And so my circuit is the 35 millihenries is the source impedance. I've got a load impedance of 350 millihenries, and I've got a bus capacitance or component capacitance for this inductor of 3200 picofarads. So one thing we need to do in this case is when the switching action occurs, we need to figure out, well, what's going to be the value of the voltage that we're going to have across that bus. So that's going to give us the initial value for the capacitance in this case. And so what I'm going to do is I'm going to look at a couple different things. I'm going to look at my current, I'm going to look at my voltage relationship. So before the switching action occurs, what we have is we've got a circuit, and if we go ahead and ignore that capacitance, basically what we have is we've just got these two inductors in series. So from a phasor standpoint, that current is the source RMS voltage divided by the net impedance, which gives us 49.6 amperes with the phase shift of 9 degrees. So if I multiply this by square root of 2 and I get this back in instantaneous format, given that I'm using a sine reference and I get the instantaneous current, we see this 9-degree relationship right here. So then we figure out, okay, now if I'm chopping at 1 amp, then what's going to be the point on wave that's going to be associated with this? And so what I want to do is I want to solve this equation for 1 amp, and I want to find out for time equals 0 what are possible angles of theta. And there's a couple different angular answers to that. There's a theta 1, which is the arc sine of 1 over the current magnitude, the 1 over 70.15, plus 9 degrees. And then there's another one, theta 2, where this is going to be 180 minus theta 1. And so basically if I have a sine waveform, there's actually two different points that could actually correspond to 1 ampere positive. All right. Now think about what chopping means. What chopping means is I've got a current, and that current is going to 0, right? So which of those 2 points could correspond to a current chopping action? Well, the first point that's on the left right here, this particular point, this can't be a chopping type of a solution because the current's going up, right? The second one is where you see the current is peaked, it's going towards zero. And then what we want to model is we want to model this point for the chop. So that would correspond to theta 1 in this case. And theta 1 is going to be equal to the, I think I have right there, minus 89.18 degrees. All right. The voltage then, so if we want to get that mapped over to the initial value of voltage at the time the switching action occurred, then what we would do is we would model a voltage divider. If that load was really, really large with respect to the source, we might not need to do this, but it looks like there's kind of like a 10-to-1 relationship, so maybe to get a more accurate value, we do that. So the voltage across the load is j omega L2 divided by j omega Ls plus L1 plus j omega L2. We multiply that by the magnitude of the source voltage. In this case, I've got this in terms of a 0 to peak value, and then this gives us the form of the voltage in this case. And you can see that we don't quite have the same voltage across the load as we do have at the source. There is kind of like a little bit of a voltage divider effect in this case. And so then for time equal to 0, if I would put in this minus 8918 degrees, then I get the initial value of voltage at the source when this current 0, when we're not, I shouldn't say current 0, but when this 1 amp chop would occur, would be minus 9256 volts. And so if we didn't model that voltage divider, this would actually be something a little bit closer to minus 10,000 volts. So it's going to make a little bit of a difference in the answer. So anyway, what this does is this gives us the value of voltage across the capacitor at time 0. Note that when the switching action occurs, that the voltage right before and right after the switching action is going to be held fixed. That's going to be an initial boundary condition. So that initial capacitor voltage is minus 9256. The current that's actually going through the breaker at that time, that's going to be the 1 amps. And basically what we're going to see as soon as that switch operates, that current's going to be transferred over to the capacitor. In order for the KCL to hold out, then this value for this initial capacitor current is going to be minus 1 amp. So it's minus what the initial through current was going through the circuit breaker. And that way, the sum of the capacitor and the inductor current then sum up to 0. So anyway, those are the boundary conditions that we're going to need to have. So just keep in mind that it's the voltage across the capacitor cannot change instantaneously. The current going through the inductor cannot change instantaneously, but the current going through a capacitor can change instantaneously. So then if I write the Kirchhoff current law relationship, current going down through the capacitor is C dV dt, current going through the inductor is 1 over L times the integral of that voltage plus the initial value of the current. I go ahead and take the derivative of both sides of the equality. I divide by C, and I kind of get this very basic equation. The second derivative of voltage plus 1 over LC times the voltage is equal to 0. There's no forcing function in this case. There's no steady state voltage. There's just going to be a transit voltage solution. So I've got a characteristic equation given by S squared plus 1 over LC equals 0. I solve for the roots of the characteristic equation, and what this does is this gives me the frequency of oscillation of the solution, 29,881 radians per second, which is about 5 kilohertz. So this is pretty high frequency. So the form of the solution is A1 cosine omega omega naught t plus A2 sine omega naught t. The initial value of voltage at 0, when I plug in for time equals 0, we see that this initial value for capacitor voltage is going to be the same as A1. So A1's minus 9256. Then the other relationship I apply is C dVc dt is going to be equal to the initial value for the current going through the capacitor. And so this dV dt value is 1 over C times IC at time 0, where IC is minus the chopped value. And if we equate this to the first derivative of this equation, the first term disappears when we take the derivative. We get A2 omega naught times cosine omega naught t, evaluate at t equals 0. This gives us A2 times 1 times omega naught, which is on the right here. And then we could use this to solve for A2. And A2 in this case is minus 10,458. Now, in the notes, when I was talking about this in the theory part, you can see that this coefficient corresponds to the chop. All right, basically what this A2 term is related to, it's related to the surge impedance times the current. In this particular case, though, we don't have that much chop current. It's only 1 ampere. And also, with respect to some other examples we've looked at, this inductance isn't really that high with respect to capacitance. And so we're not getting as much of a chop effect as if we had, like, say, some larger value in henries for that inductor. But I just kind of wanted to show you, what would happen if we had a smaller value of that inductance, how that would change the way we would work this problem. So this A2 term's not as big as maybe what we would see if we had, say, like a big transformer inductance being switched out. So anyway, when we plug in for A1 and A2, we get this form for VC. Note that it has a cosine form and a sine form, and then what I do is I convert this over to polar coordinates, and I get this in terms of a cosine with a magnitude and an angle. And this more easily allows me to see what the peak value for the voltage is going to be. So when you're doing something like this, basically if you think about working this out in terms of complex numbers, you could think about taking an imaginary value of minus 9256 plus J 10,485 and convert that over into polar. The reason that I would have to make a sign change here on this coefficient is because sine lags cosine, and so I have to make a sign change there if I wanted to figure out what this term and this term were going to be in terms of a magnitude and angle. The next thing is to take a look at what's the impact of putting some additional resistance in here. Say if we put some resistance in here, let's say it was 10K, what difference would that make? And we know it's going to add some damping in here, but then how much damping is it going to add? So whenever you run into this, and if you want to make assumptions, it's always a good thing just to double check your assumptions. And so the one thing I would want to check out first is, this change my initial conditions? Does this change what I would have for the initial value of voltage across the capacitor at the switching time? With no resistance in the circuit, we have a load reactance of J 131.95 at angle 0 degrees. If I put this 10K in parallel with the existing reactor, then the parallel combination gives me 131.94 at angle 89.2 degrees. All right, so not really too much difference in here. And so I can kind of ascertain from this that putting that resistance in the circuit's not going to change my IC calculations by anything that's worth considering in this case. So whenever you're doing this and you do have a situation where you do have some resistance, just double check to see if the assumption holds. Don't just say something like, well, this resistance is large and it doesn't make any difference. I mean, just do a more quantitative check and just verify that if I include that resistance in there, it wouldn't make any difference, rather than just saying it's large and ignoring it. So given that we've double checked to make sure we can neglect R in the initial conditions, I'm just going to go ahead and use the same initial conditions as before. where basically what I'm going to assume that I'm going to have the same value for the capacitor voltage. And then I'm also assuming that all that charge, I'm sorry, not all the charge, but all the current going through the circuit breaker when the chopping occurs gets transferred over to the inductor, capacitor, I'm sorry, to the capacitor. Why is that a good assumption? Because basically, if I have a change in this current, the current going through the inductor can't change instantaneously. The current going through the resistor can't actually change instantaneously either, because that's going to be related to the capacitor voltage divided by the resistance. And so due to the fact that that capacitor voltage can't change instantaneously, that means that the resistor voltage, when they're in parallel, can't change instantaneously either. So that basically means that this 1 amp gets transferred over to that capacitor in order to make sure that we still have Kirchhoff current law satisfied at the node. So as far as writing the differential equation, what changes in this case, we have an additional term for the current going through the resistor. Now what we have is we have a first derivative in the equation. That coefficient's 1 over RC, so this is going to give us some possibility for damping. When I look at the roots, basically I get a real part, which is minus 1 over RC divided by 2. It does kind of detune the frequency a little bit. It's still about the same, but it detunes it just a little bit. But now when we look at the form of the solution has an exponential associated with it. So go ahead and apply the boundary conditions, the initial conditions. I still get an A1 value of minus 9,256. Now when I look at the chop value, basically I'm going to get something kind of similar to what I had before, where this change in voltage with respect to time is going to be 1 over C times the chop value, because that capacitor kind of absorbs the current change. One thing that's kind of interesting about this is that amount of current that's getting chopped, if we ignore the initial capacitor current, is basically related to both the inductor current and the resistor current. So basically, if you look at the current actually going to the inductor when you have the 1 ampere chopping, that current actually going to the inductor in that load was actually 1.9256 amps, and then the current that was going through the resistor was minus 0.9256. All right, so one thing that's sort of interesting I want to point out, because we're going to be looking at the PSCAD solution, is when we have the resistor in the circuit, since that's a kind of a low value of damping resistance in this case, it does actually have a little bit of current in there, which means that we don't have an inductor current, which is the same as a circuit breaker current. This chopping value of current is so small that the resistive current does kind of play into this a little bit. But anyway, you get this coefficient for dV/dt in this case, and then if you go through the math on this, you get a value for A2, kind of similar to some of the problems we've worked before. This is minus 17,948, and so now you plug everything in, and just like I had a cosine plus a sine, and I switched everything over to a cosine, I'm going to do the same sort of thing here. And then this is going to be the form of the solution. So you have what kind of looks like a larger magnitude, it has a pretty large magnitude term, but the thing you have to keep in mind, that's being multiplied by a rapidly decaying exponential, because that alpha term is so large. In fact, it's so large that when you kind of take the normal way of figuring out what this peak value would be as far as approximation, where you look at when cosine is plus or minus 1. So if you actually go through and figure out the time associated with that, if you use that methodology when this argument's pi, you're going to get a peak value of about minus 10.3 kV. However, when later on we look at the PSCAD simulation, that needs to be that's going to be minus 12.3 kV. So we're off, right? The reason we're off is that this is such a damped problem. So when I plot this out, this actually shows the plot, which shows the, if I plot this particular expression, this actually shows it does get to about minus 12.3 kV. And so this answer right here does match up with the PSCAD simulation. It's just that this is decaying out so fast that this method we would typically employ to get the peak value, finding the time corresponding to pi in this case and plugging in for time, doesn't work as accurately because you can see this is just damping out so fast. In fact, it doesn't even really oscillate any. It has kind of what looks like the start of an oscillation, and then right away it damps right out to zero. And so we're kind of right on the edge in this case of having this be underdamped versus overdamped. We're pretty close to the point where we went and had imaginary roots in this particular problem. We would just had two decaying exponential terms. All right. So anyway, we'll take a look at what this looks like in PSCAD, but this is a little bit more challenging in the sense that what you guys had to do is do some extra work because this value of L2 was only about 10 times greater than the source impedance. I haven't marked LS, but I've also been referring to it as L1. But you got a significant voltage drop, and so you just simply didn't have the source voltage across here. You had to take some voltage drop into account. And so this is a little bit more of a generalized technique that's gives us a little bit more accuracy for comparing to simulation. So next what I'll do is we'll take a look at the PSCAD results.